Hello everyone, my name is Marlene de Ruiter and I'm an assistant professor in multi-risk at the Institute for Environmental Studies at the VU University Amsterdam. The photo in the background was taken in Afghanistan during a recent flood event. The country is often hit by disasters. Historically, flooding is the most frequent occurring hazard type, while earthquakes are the most damaging hazard in terms of fatalities. What you also see in the photograph is that the majority of the residential buildings, as you see here, are made out of adobe. This is the case for 50% of the population living in developing countries. Adobe buildings are, however, very vulnerable to the impacts of most natural hazards. Traditionally, building-level disaster risk reduction measures are aimed at a single natural hazard, despite the fact that in many countries, the society faces the threat of multiple hazards. During its 2019 global platform, the UNDRR called upon the science community for an increased understanding of the complexities of multi-hazard risk. For example, building-level disaster risk reduction measures that aim to decrease the vulnerability of one hazard can actually have opposing or conflicting effects on the vulnerability of another hazard. We define those potential adverse effects of DRR measures as asynergies over DRR measure. An example is that of houses along the California coast that are often built on stilts to prevent them from flooding. However, building on stilts also makes them a lot more prone to damages from earthquakes. So DRR measures aimed at reducing the risk of one hazard can have an adverse effect on the risk of another hazard and maybe even increase the total risk, as depicted here in the figure by the purple line, both on the left and on the right panel. What you see on the left is that the total risk decreases when a flood DRR measure is implemented, while on the right, the total risk increases with the implementation of an earthquake DRR measure. We studied this concept of DRR asynergies in a case study of Afghanistan, where we assessed the impacts of asynergies between flood and earthquake DRR measures per district. Due to the ongoing conflict, there's only limited data available for the country. Therefore, in this study, we used data collected by the World Bank for their 2017 Afghanistan multi-risk assessment. The data included information on all types of residential buildings and their material types. Examples of those are shown here in the picture. We first calculated the average annual losses for each hazard in the current situation and then designed two hypothetical DRR scenarios. We used this to identify these asynergies, so districts for which the DRR measures of one hazard increase the risk of another hazard. So in the flood DRR scenario, we upgraded all adobe buildings to brick buildings. And with such an upgrade in building materials, floodwaters can less easily infiltrate, while due to the increased stiffness of the building, they are much more prone to damages from earthquakes. In the earthquake DRR scenario, we upgraded all adobe buildings to wood buildings. Due to increased buoyancy, they are more prone to damages from floods, while the use of wood allows buildings to kind of sway along when an earthquake wave makes them less prone to earthquake damages. With such an upgrade in building material, the value of the exposure increases significantly. Therefore, we used relative average annual losses, so the ratio of the average annual losses versus the value of the exposure. We calculated the average annual loss ratios 4 times for flood risk in the flood DRR scenario and earthquake risk in the flood DRR scenario, and for both risk types in the earthquake DRR scenario. In the map, the districts in blue are those where the sum of the flood and earthquake risk ratios are lowest in the flood DRR scenario. And in red are the ones where earthquake DRR measures cause a lowest total risk ratio. The color gradients show the percentage and risk reduction of one DRR scenario over the other. So the deeper the color, so the deeper red districts, for example, are those where the percentage reduction in risk ratio is much larger in the earthquake DRR scenario. And in blue, you see the districts where the flood DRR scenario results in a much larger percentage reduction in risk ratio. The less darkly colored districts would be impacted both positively and negatively to a much lesser extent from either one of the DRR measures. The map also shows that a large part of the country would benefit from flood DRR measures, basically this whole part on the west. But it also shows that some of the districts where they would benefit from earthquake DRR measures, there's a much higher benefit. For example, in Bak and in Khoshtvart-Viering. The reduction is almost around 40%, while the highest risk reductions of flood DRR measures, such as in Sipho and in Kamart, are around 15%. The aim of our study is to demonstrate to scientists and policymakers the importance of accounting for DRR asynergies in risk assessments, much rather than providing a policy recommendation for the Afghan government regarding its risk management. Although decreasing the vulnerability of an entire country's building stock to better withstand natural hazards may appear unrealistic, it does enable us to better understand the interactions between the different DRR measures aimed at a single hazard, and it provides us insights into the potential asynergies of DRR measures between different hazard types. This is only one part of trying to better understand the complexities of multi-hazard risk. In our study, we only looked at flood and earthquake risk, and we looked at them separately, so we didn't even account yet for the effects of a disaster on changing vulnerability during a next disaster. Future research should continue to better understand the spatial and temporal dynamics of risk.